again Samantha Burnham and not Larry Ward. Elecsys CSF biomarker immunoassay demonstrate concordance with results of the Amyloid-PET imaging in AIBL patient samples.
Hello again. So Larry sends his apologies. He couldn't be here to make the presentation today, and neither could James, so I get to give two. So I hope you'll understand that these aren't my slides and it's not my talk, so I'll do my best to deliver the information to you, and I may have to field some questions back to Larry and James afterwards if I can't answer them. I think we're preaching to the choir here, so there's some details about the prevalence and the cost of Alzheimer's disease, and I guess the take-home message is that it's just as much of a concern for us in Australia as it is for everyone else around the world. Another one here that I think you'll all be pretty familiar with, and this is just to make the point that the biomarkers that we're concentrating on are those associated with amyloid and tau. So there's been some recent well-established biomarkers associated with amyloid pathology, starting off with the A-beta PET. FDA have got an approved visual read that can be used in clinical trials, and we've also now got the continuous SUVR measures. More recently, CSF has been making an appearance with biomarkers for A-beta 1 to 42, A-beta 1 to 40, the total tau and the phosphorylated tau. And there's been a lot of publications showing good concordance between these imaging measures and the CSF measures. And there's the schematic there from Jack showing how it's thought that those different types of biomarkers progress throughout the disease. So in terms of those publications, there's a couple showing that relationship with the Elecsys immunoassay that I was talking about previously, and I'm again presenting on here. So Oscar Hansen had a paper in Alzheimer's and Dementia looking at the relationship between amyloid-PET and the Elecsys CSF biomarkers on close to 300 of their BioFinder participants, as well as about 650 of the ADNI participants. Schindler also had a publication in the same issue looking at about 200 participants from the WashU cohort. And what they found was that there was a high ability of the CSF biomarker ratios, so T-tau to A-beta 42, as well as the P-tau to A-beta 42 and the A-beta 42 to 40 ratios, to detect the abnormal PET imaging outcomes. So the AUC was over 92% in all of those studies. The single biomarkers didn't perform as well as the ratios. A-beta 42 was the best performing of the three single biomarkers, and the tau CSF markers had slightly lower efficacy. So here we're looking to do the same type of analysis, but with the AIBL subjects. So again, assessing the concordance of the imaging and the CSF biomarkers. Those of you that are really paying attention will notice that there's 202 participants listed here instead of the 200 I had earlier. I removed 2 participants from my study because they were diagnosed with FTD. We have the study endpoint, as I was saying, is whether they were amyloid positive or abnormal for amyloid based on the PET imaging. We looked at data from 3 different traces, so Pittsburgh B, fleet metamol, and florbetapia. And we also looked at we used the thresholds from the native traces to define whether they were abnormal or normal. This is the study demographics, so you can see that the majority of our sample, again, is cognitively normal at 140, that 33 and 27 for MCI and AD, and those 2 FTDs I was talking about. We see increasing levels of ApoE carriage in the MCI and AD, as well as across the amyloid positives and negatives, and there's a few other significant differences there which you can all see. So here we're looking at A-beta 42 and the A-beta 42 to 40 ratio. The cutoffs were defined in the top left-hand corner using a natural cut, so that's where the 2 distributions cross. And then we also looked at an optimized Yadens index, and so this is where we used supervised classification, so we use the actual PET images to define those cutoffs. You can see the thresholds in the table for the individual biomarker and the ratios, and we can see that the A-beta 42 to 40 ratio with the optimized cutoff has the highest sensitive PPA and MPA, and similar for that with the natural cut, with A-beta 42 performing slightly worse. And that's again shown in the top right-hand ROC curves. The pink line represents the single biomarker and the green line the ratio. The same setup of slides for the t-tau to A-beta 42 ratio. Here we see some slight differences between the cutoffs between the natural cut and the optimized cut, so 0.26 to 0.14. The performance is somewhat better using the optimized cut, and again, both of those ratios outperform the single biomarkers. In the top right-hand corner for the ROC plots, the blue line represents the tau, the pink magenta line, the A-beta 42, and the green line, the ratio. And I'm going to repeat myself again through these slides. Here looking at p-tau to A-beta 42. More similar alignment between the natural cut and the optimized cut here at about 0.02. The PPAs and MPAs are very similar, and again, those ratios outperforming the single biomarkers. And we can see the AUCs, so we can see the ROC in the top, where the A-beta 42 and the p-tau are performing quite similarly, and the ratio doing a lot better. In terms of clinical diagnosis, we looked at what these levels were like. So the black box plots represent the normal amyloid, people with normal amyloid scans, whereas the grey ones represent those with abnormal amyloid scans by PET. We can see that there's certainly differences between the positive and negative amyloid scanned people in the normal controls, not so much in the MCI, and definitely in the AD for the A-beta 42 plot on the left. But when we look at the ratio, those differences are really magnified. Again, the same plots for t-tau and the t-tau to A-beta 42 ratio, and we can see that dramatic improvement in stratification between the amyloid positives and negatives from the PET scans on that right-hand side plot with the ratio. And another one, so here's the p-tau to A-beta 42 ratio, and we get very, very similar findings here. So looking at the continuous PIB SUVR, so here we're down to 90 subjects, just those that were analysed using the Pittsburgh B compound, and we can see that we get some good stratification between those in blue, who are considered to be amyloid negative on the PIB scan, and those in red who are considered to be positive. And we see that clustering across all of the different biomarkers. Again, those clusters seem to be a little bit more pronounced when we look at the ratios on the bottom as opposed to the individual biomarkers at the top. This is an overview of the results, so you can see the different thresholds that are proposed based on these findings, the AUCs, PPAs, MPAs, PPVs and MPVs accuracy for the individual biomarkers as well as the ratios. And we can see here that the ratios all perform very similarly to each other and certainly outperform the individual biomarkers. And this is really consistent with what's already in the literature, so those two publications that I was talking about from Oscar Hansen and Schindler. And also we repeated this analysis in our cognitively normal population, and we got very, very similar results. So to summarise, we've looked at CSF biomarkers from 202 participants in the AIBL study using the Roche Elecsys immunoassay. Predominantly, we were looking at cognitively normal population. 70% of the population we were looking at were cognitively normal. And 42% of all participants, or 27% of our cognitively normal, had positive amyloid PET results. We saw really good concordance between the Elecsys CSF biomarkers and those PET measurements, particularly for the ratios with A-beta 42. The best performing single biomarker was A-beta 42, but again, not as good as the ratios. Overall agreement to PET at the optimised thresholds was close to 0.9 for the different ratios and about 0.8 for the single biomarkers. We found similar results, as I said, when we looked at just the cognitively normal participants, and these are consistent with other publications in the literature. I'd like to acknowledge everybody again from AIBL, particularly the study participants and their families, and all of the study partners involved with AIBL and this study. So thank you very much again.
Is there any question? So thanks a lot. We have to move because for the next symposium. Next symposium, number 7.